look at the spectroscopy of aromatic compounds. We already looked at the infrared vibrational frequencies, and we said that the CH stretch of an aromatic shows up slightly above 3000. We have overtones between 1700 and 2000 reciprocal centimeters. Then we have carbon-carbon double bonded stretch at 1450, 1500 and 1600 respectively. And then we have the CH bend, which is characteristic of substituted benzenes, between 690 and 900 reciprocal centimeters. And this is just a typical infrared spectrum showing the diagnostic peaks. With NMR, because of the anisotropic effect of an aromatic ring, we know that aromatic rings produce this significant deshielding of the protons. So these protons are heavily deshielded. They're deshielded. See that the shielded protons, and as a result they show up very downfield between 6.5 and 8 parts per million. Now, even though aromatic peaks can be very complex or complicated because of long range splitting, right, the best way to determine the number of protons that are present in any aromatic NMR signal is by integration. So by simply integrating the aromatic signal, you'll be able to tell how many protons are responsible. As you can see, when you have one singlet, you have 4 protons. It tells you that you have 4 chemically equivalent protons. And then if you have 2 different types of protons, then you're going to have doublets, because this will be split by this into a doublet, and this will be split by this into a doublet. So you're going to have 2 different doublets. Okay. Now, if you have 2 signals, right, in which case, if you have maybe a para disubstitution, in this case you have para, you know that all these protons, they're going to have 2 different carbons. I'm sorry, this is for carbons. You're going to have 2 different carbons. This is for the C13. You're going to have 2 different carbons. You're going to have 1, 2. And then here you're going to have 3 different carbons. And here you're going to have 4 different carbons, depending on what you have. And here you're going to have 6 different carbons. And here 6 different carbons as well. See? So you should be able to tell how many signals, how many carbon signals are present, depending on the type of substitution that is present in the aromatic compound. This is something we learned in Chem12B. So you should be able to tell how many aromatic carbon signals will be present. Let's talk about graphite. Graphite consists of layers of sheets of fused aromatic rings. Buckyballs are C60 spheres made of interlocking aromatic rings. You see, each of these aromatic rings is aromatic on its own, but overall, the buckyball is non-aromatic. Fullerenes, on the other hand, come in other sizes of C70. See, and we know that buckyballs are only aromatic because you're looking at individual rings. You see, they're looking at individual rings are aromatic. We have individual buckyballs are made of individual aromatic rings. Now fullerenes, which is C70, can be made into tubes or cylinders, nanotubes. We have single, double, and multi-word carbon nanotubes, and these have many applications in things like conductive plastics, energy storage, conductive adhesives, molecular electronics, thermal materials, fibers, fabrics, catalyst support, biomedical applications. So fullerenes are just means of delivering things like catalysts to reactions, in very, very, very tiny amounts. Anyway, that's the end of this chapter. So we will continue with chapter 19, where we'll start talking about electrophilic aromatic substitutions.